Hi, today let's discuss some problems using Poisson brackets. We'll do some examples, problems, and also include the previous year questions. Some of the problems I may leave as an exercise, even though the solution is already given in your notes. The first one is an example. We need to show that if phi comma psi is a Poisson bracket, then prove that the partial derivative of this Poisson bracket, the partial derivative, behaves like this. It looks like the product rule. You know the product rule. If you have something like dou by dou t of uv, where u multiplied by v, then you have u multiplied by dou v by dou t plus dou u by dou t multiplied by v. That's the product rule. We also call it the Leibniz rule. Alright. So the Poisson brackets obey a similar rule with respect to partial derivatives. That's what we need to prove now. Okay. So we need to find the partial derivative of the Poisson bracket phi comma psi. Okay. So for this one, right, we'll use the fundamental definition of Poisson bracket, and remember that throughout this thing we'll always use the Einstein summation convention, which means that there is a summation over repeated indices. Right. Now for this one we'll use the fundamental Poisson brackets. Right. But you need to remember that for most of the problems, using Poisson brackets, you can actually solve them without using the fundamental definition of them. Right. You can also use the fundamental definition, but most problems can be solved without using the fundamental definition. Right. This is one of the problems where using the fundamental definition is convenient. Right. So first we start with the Poisson bracket phi comma psi. Right. You remember this is the definition. You take the partial derivative of the first one with respect to q, the partial derivative of the second one, right, the second one with respect to p, and then interchange this q and p with a minus sign. Right. Interchanging q and p costs a minus sign usually in classical mechanics. If you have noticed, in the Hamilton's equations, you can interchange q and p, but then you get an extra minus sign. All right, it's the same minus sign that appears here. It's the same minus sign that appears here. Okay? And there is actually a summation over k. There's actually a summation over k. All right, so this is the Poisson bracket. Right. Now we take the partial derivative, partial time derivative. We see that for each term we can use the product rule. Right. For each term we can use the product rule. So first we take this, okay, and we use the product rule. We also make use of the fact that the partial derivatives can be interchanged. Okay, this means that if you have something like dou by dou t of dou phi by dou qk, okay, you can also write it as dou by dou qk of dou phi by dou t. Right. Actually, the result that we are going to prove depends on this interchange. We can actually make this exchange for a partial derivative. Right. But for a total derivative, we cannot always do that. Okay. It's a bit more tricky. For a partial derivative, we can always interchange the order of taking the derivative. Right. So when we take dou by dou t of this thing, okay, we are taking dou by dou t of the first term, and we use the product rule. Also, we interchange the the order of taking partial derivative with respect to q, k and t. That's what we do here. This is the derivative of the first term with respect to t, okay, and then we have interchanged this q and t. Okay, so this term becomes, so you have to use the product rule. So you get two terms from this one. It's dou by dou qk, dou phi by dou t, dou psi by dou pk, plus dou phi by dou qk. You keep this term intact and take the time derivative of the second term, right, using the product rule, the usual product rule. Okay, so that's dou phi by dou qk, which is here, and then dou by dou t of dou psi by dou pk. Okay, dou by dou t of dou psi by dou pk, which can be written as dou by dou pk of dou psi by dou t. All right, so what we are using here is we have a term from here, dou by dou t of dou psi by dou pk. All right, and that can be written as dou by dou pk of dou psi by dou t. All right, now we have only dealt with the first term here. The first term gives these two terms. All right, I repeat, we have done two things. We have used the product rule, and we have made use of the fact that the partial derivatives, the order of taking a partial derivative, can be interchanged. Right? Now we need to deal with the second term. We do exactly the same thing with the second term, and we get there's a minus sign here, so we get a minus sign here. Right? So we can just look at it. First you take the partial derivative with respect to time of the first term here, and that gives you dou by dou pk of dou phi by dou t. We have interchanged, multiplied by dou psi by dou q, minus, because of the minus sign here, dou phi by dou pk and dou by dou qk of dou psi by dou t. Right? That's what we have done. Okay. Now we can easily combine terms. If we look at this, this is dou by dou qk dou phi by dou t, dou psi by dou pk, and let's look at the second term. It's dou by dou pk of dou phi by dou t, dou psi by dou qk. Alright. So if you look at these two terms, it just exactly looks like a Poisson bracket. Similarly, these two terms also look by a Poisson bracket. You just use the fundamental definition. Alright. So instead of phi here, if you have dou phi by dou t, so instead of phi here, if you had a dou phi by dou t, okay, let's say, right. So instead of phi this, okay, instead of phi here, if you had a dou phi by dou t, okay, yeah, instead of phi, if you had a dou phi by dou t, then you would have a dou phi by dou t here, okay, and a dou phi by dou t here. Right? That's exactly what we have here. Dou by dou qk, dou phi by t. So this first term, sorry. So this first term, the first term we can write as dou phi by dou t, comma psi. Fine. Right? What about the second term? This is dou phi by dou qk, dou by dou pk of dou psi by dou t, minus dou phi by dou pk, dou by dou qk, dou psi by dou t. Alright. So this is simply phi, comma dou psi by dou t. Alright. That's exactly what we are asked to prove. Right. So taking the partial derivative of a Poisson bracket is very similar to using the product rule for partial derivatives. Okay. So this result is not particularly difficult. We have used the fact that the partial derivatives can be interchanged. Alright. Now the case of total time derivative is not that simple. Right. The case of total time derivative is not that simple because you cannot always interchange a total time derivative and a partial derivative with respect to something else. Alright. So you have to be more careful, but still it can be seen that the same result holds. Okay. If you have d by dt of f comma g, you take the derivative of the first one, Poisson bracket with the second term, plus the Poisson bracket of the first term, plus total time derivative of the second term. Right? The result looks exactly the same, even though proving is a bit more tricky. Okay. Now here there are different ways to do this. Here we won't be using the fundamental we won't be using the fundamental definition, but we will be using the fact that df by dt is actually, we know the fact that df by dt is equal to Poisson bracket of f with h. Okay. Not only that, there is also time derivative here. So df by dt is Poisson bracket of f with h plus dou f by dou t. So here we have a partial derivative. Okay. Alright. So we can use the first result. We can make use of the first result. Right. So this is what we are going to do. So we'll see. Let's check. Okay. D by dt of f comma g, we can write. This is the total time derivative of something, some quantity. Alright. So this we can write as d by dt of something is actually f comma g. We are taking the total time derivative of something. Alright, the total time derivative of something is, alright, that something combined with the Hamiltonian, am I right, plus the partial time derivative. Alright, this is the rule for finding the total time derivative. Anything, alright, this could be some other function. This Poisson bracket with f comma g could be some other function. Let's say capital F, or it could be some other function. Let's say y. Okay, this could be some other function y. So you have got d by dt with d by dt of y. And what's d by dt of y? It's a Poisson bracket of y with the Hamiltonian plus partial time derivative of y. Okay, that's the rule that we have used here. Okay, all right. So that's what we have done here. It's f comma g with h plus dou by dou t of f comma g. Okay, I hope that's clear. Now we make use of the Jacobi identity. What does the Jacobi identity say? The Jacobi identity says that see, if you take the cyclic permutation of all these double Poisson brackets and add them, you should get 0. Okay, how do we take the cyclic permutation of this? How do we take the cyclic permutation of this? The first term is of course f comma g comma h. What's the second term? What's the second term? For the second term, what we do is we start from here. It's g h f. Okay, plus g comma h. Okay, g comma h comma f. Right, so you go in this order. Plus, what's the third term? Third term, you start from here. It's h comma f comma g. All right, h comma f with g. Okay, this is 0. This is the Jacobi identity. This is known as the Jacobi identity, which we saw in the previous class. Right, so f with g with h, gh with f plus h with f comma g. This is equal to 0. Right, this means that this fg with h here, this fg with h here, we can write as fg with h is equal to minus g comma h comma f plus Poisson bracket of h comma f with g. All right, the double Poisson bracket. All right, so we use this result and we say that f comma g with h is equal to minus g comma h comma f minus h comma f comma g. All right. So that's the thing we are using. Now we'll substitute this here. We shall substitute that here. And what do we get? We get d by dt of f comma g. We just substitute that term here, right? Plus dou by dou t of f comma g. All right. Now what do we do? This dou by dou t of f comma g, we already know that it's dou f by dou t comma g plus f comma dou g by dou t. This was our previous result. Okay, we have made use of that. So we just, in this step, we only use this result. Right. Now what do? We see that there is a g comma h with f here. Okay, and what else do we have? We have got this term can be written as minus, because of the antisymmetry. This term can be written as minus dou g by dou t comma f. Am I right? Right. That's what I've done here. I've combined these terms, minus g comma h with f. That's exactly this term, and this I have brought here. It's minus dou g by dou t. It's dou, okay, minus dou g by dou t comma f. Right. Then I combine the other term plus f comma h comma g. This term comes exactly there, and this you write exactly like that. Okay, dou f by dou t comma g. Right. Now we use the distributive rule, the distributive property of the Poisson bracket. All right. So if you have something like this, there are two things with f. Right, so we can write that as, you take this minus outside, this is g comma h plus dou g by dou t comma f. All right, this is the distributive rule. If you have something like a comma b, okay, a comma b, sorry, if we have something like a plus b comma c, all right, this was the distributive property. This is a comma c plus b comma c. Right. So if you have something like a comma c plus b comma c, you can write it as a plus b comma c. That's what we do. All right. We have got a comma f and b comma f. So you can write as a plus b comma f. That's what we do here. Right. And instead of a here, we have got a g comma h. That's all. And this minus we pull out. Okay. So that minus is here, and it's g comma h plus dou g by dou t, right, comma f. Fine. Plus the same thing we do here, right? Because this is both these things Poisson bracket with g. Both these things Poisson bracket with g. Right? So this we can write as f comma h plus dou f by dou t comma g. Right? We have used the distributive property. Now what is g comma h plus dou g by dou t? This is simply dg by dt. Am I right? This is simply dg by dt. And there's a minus sign here. So this is actually dg by dt comma f, which is with the minus sign, so you can change them. So it's f comma dg by dt. Okay, I hope this is clear, because we know that dg by dt is simply g comma h plus dou g by dou t. That's exactly what we have here. That's exactly what we have here. Okay. All right. So there's a minus sign, so you can bring that f here. So it's f with dg by dt plus, similarly, this is simply df by dt comma g. Alright. So even though the proof is not quite straightforward, the result finally is the same. Okay, we have used the Jacobi identity and the distributive property of the Poisson brackets, and we see that d by dt of f comma g is f comma dg by dt plus df by dt comma g. Okay. Here is another example involving angular momentum Poisson brackets, all right. So find the Poisson bracket of Lx comma Ly, right, where Lx and Ly are angular momentum components, right. So angular momentum we are familiar with. This is like the one of the functions that we discussed earlier. It's a function of both q and p. Okay. So angular momentum L vector is equal to r vector cross p vector, and Lx is equal to, okay, you know how to get the components of it, all right. You can do the determinant thing for the cross product, and we know the components, all right. We know the three components. Lx is ypz minus zpy, Ly is zpx minus xpz, and Lz is xpy minus ypx, all right. So let's first find Lx with Ly. Let's first find Lx with Ly. Okay. So I hope this is an exercise, all right. Find the components. Find the components. Find the components. You know how to do that, all right. You know how to find the components of A vector cross B vector. You can either use the Levi-Civita symbol, or you can write down the determinant and find each component, all right. So it's an exercise. So I tell you that these are the components. Okay, we have written this R cross P, three components of R cross P. R cross P is a vector. I've written down the three components here, Lx, Ly, and Lz. Okay. All right. So Lx with Ly. Let's first find Lx with Ly. So it's ypz minus zpy, comma zpx minus xpz. Fine. Right. Now we can use what we call the distributive property and the other properties, and we can write them down like this. It's ypz, comma zpx. Fine. All right. And minus, okay, there's also a second term here. So you take the first term and combine it with both these terms. All right. So it's ypz with zpx. That's this term. And ypz minus. So there's minus here. So it's minus ypz, comma xpz. Fine. Okay. And then here there's this minus which can be pulled out. That's I pulled out. And zpy with zpx. Okay. And zpy with xpz, all right, but there's an extra minus in here, so it becomes plus zpy, comma xpz. Okay, that's what we have done. Now look at this. We need to solve all these brackets, all right. So let's look at the first one. Okay, let's look at the second one. It's ypz, comma xpz. Let's look at the second one. What's the value of this? All right. So it's a good thing to remember the fundamental Poisson bracket relations, which says that if you have something like qi with pj, it's delta ij. Okay, there's also something else. Qi with Qj is 0, and Pi with Pj is also 0. All right. So the only non-zero commutator here, only non-zero commutator is if I is equal to j. I hope this is clear. This means that x with Px is equal to 1. Okay, and x with Py is 0. Similarly, Px with Py is 0, Py with Pz is 0, x with Pz is 0, y with Py is 1. Okay, so we can use that result. So if you look here, let's take the first term, and the combination would be y with x, which is 0, and then there will be y with Pz, that's also 0. Okay, and from here we can combine Pz with x is 0 and Pz with Pz is 0. So the first term is simply 0. Okay, I have expanded it here for your sake. You can check this. Okay, what about this term? We have got z with z 0, z with px 0, py with z 0, py with px is also 0. Right? So we can actually expand this term, and all the terms appearing will be 0. All the terms appearing will be 0. Okay. What about zpy, comma xpz? Here there is a non-zero commutator. Okay, this is z with x is 0, but z with pz is non-zero. Z with pz is non-zero. Py with x is 0. Py with pz is non-zero. Right? So there is just one non-zero commutator here. So not commutator, I'm sorry, it's Poisson bracket. There's one non-zero Poisson bracket here. I'm sorry if I mix up this commutator and Poisson bracket terms in between. I hope you will correct it. Right? When you listen to it, you have to correct it in your mind. Okay. So this thing, there's a non-zero commutator, sorry, a non-zero Poisson bracket here. It's z with pz, which is equal to 1. So let's just take the non-zero Poisson bracket. Let's just take the non-zero Poisson bracket. All right. So this is z with pz. Okay. And there are two extra terms. It's pyx. So it should be here. All right. So in quantum mechanics, when we are doing commutators, we have to be careful about the order, as I have told you. But in this case, there is no problem. All right. You can just write. So it's z with pz and then pyx. Okay. You can pull this py from here and you can pull this x from here. Let's not worry about the order. So z with pz is 1. So this is simply pyx. This is simply pyx. Right. What about this? Similarly, we did not check this one. Is there any non-zero Poisson bracket here? Yes, because y with z is 0, y with px is also 0, pz with z is 1. Not 1, it's minus 1 actually. So this is actually, there's a pz with z here, and the other two terms also have to be there, y, px. And what's pz with z? Z with pz is 1, so pz with z has to be minus 1. So this is minus ypx. Okay, so it's minus ypx. And this is, yeah, this is pyx. All right, this is minus ypx and this is pyx. So we can actually combine them, and what do we get? It's actually xpy minus ypx. All right, xpy minus ypx. The final answer is xpy minus ypx. Okay, and what's xpy minus ypx? It's simply the z component of angular momentum. Xpy minus ypx. All right. Now I have rushed through the proof by suggesting you to take only the non-zero Poisson bracket. All right. If you are not quite sure about it, you can go through the problem and see that this indeed is the case. All right. This indeed is the case. You can check this. If you are not completely sure about my steps, you can check. I think I have given it in a more detailed manner in the presentation. You can check that. You can check your notes. If you have any questions, please ask. All right. You also may make use of this thing. Okay. We have seen that AB with C. I have given this to you in the last class. AB with C is actually A comma C with B plus A multiplied by B comma C. All right. This we have already seen. Okay. So we can actually use that to prove. Another result. If you have something like AB with CD. Okay, AB with CD. Right. This means that you have to take all combinations, A with C, A with D, B with C and B with D. You have to take all combinations. All right. So the answer is, it's actually A comma C multiplied by BD. You can use the previous result to prove this, plus A comma D. Okay, you take this combination A comma D and you have left out BC. Okay. As I said, in the case of commutators, you have to be more careful. These are Poisson brackets, so let's not worry about the order. Plus, then you go for B, BC, AD. All right, this is B comma C, and what did we leave out? It's AD. Okay, plus you have got B comma D, B comma D, B comma D, and what have we left out? It's AC. All right. So this, I want you to prove this result. Okay, this is also an exercise. I want you to prove this result. All right, I ask you to prove it so that you get more practice manipulating the Poisson brackets. All right, and when we do quantum mechanics, this practice will actually help. All right, immediately after doing this Poisson bracket things in quantum mechanics, I will be discussing commutators. All right, there are so many problems involving commutators, so we'll discuss those things. Right. In the case of commutators, we have to be careful about this order. All right. So we have to be careful because we have done A comma C, right? A comma C, and we have simply written BD without worrying about the order. Okay, when we do the commutator, you'll see that this B should come here. Right? We have to be a little bit more careful in the case of commutators. All right, so I want you to prove this result. Okay, or I want you to simply find the result AB with CD. Okay, so please do that as an exercise. So what do we have here? We have Lx with Ly is equal to Lz. Lx with Ly is equal to Lz. Okay. Similarly, you will see that Ly with Lz is equal to Lx. You can prove these things exactly in the same manner. So these are all left as exercises for you. Okay. Prove that Ly with Lz is equal to Lx and Lz with Lx is equal to Ly. So you see that there is some sort of a cyclic permutation here. All right. If it is Lx with Ly, then it's the third one. It's Lz. Okay, it is Lz, right? And if you do Ly with Lz in the cyclic order, in the cyclic permutation, then it is Lx, right? Similarly, if you do Lz with Lx, it is equal to Ly. You can do it in different order and then you will get extra minus signs. Alright, so these are the things. Now these results, these results that we have found here can be summarized in a very elegant manner using what we call as the Levi-Civita symbol or Levi-Civita tensor. Alright, I hope you are already familiar with Levi-Civita tensor, but for the sake of completeness, let's just discuss. Alright, so this Levi-Civita symbol, it has 3 indices and it is 0 if any of the 2 indices are the same. Right, it's 0 if any of the 2 indices are the same. It means to say that it's a completely antisymmetric tensor in a way. Alright, it's not exactly a proper tensor, but you might have seen these things. It's completely antisymmetric about its indices. It's not exactly a tensor, so let's not use the term tensor here. It's completely antisymmetric about interchange of any 2 things. So if you interchange I and j, you'll get an extra minus sign. If you interchange j and k, you'll get an extra minus sign. So any interchange will give you an extra minus sign. Alright, so this means that if any 2 of the indices are the same, it's equal to 0. Alright, so all these things are 0. Okay, and epsilon ijk is 1. Alright, so the only possible non-zero values are 1 and minus 1. If ijk are distinct and in cyclic order, then it's 1. For example, if you have something like epsilon 1, 2, 3, it's equal to 1. Right, and if it's in a non-cyclic order, for example, actually this is the only thing that you need to remember. Okay, actually epsilon 1, 2, 3 is equal to 1 or epsilon xyz equal to 1. This is the only thing you need to remember. Why? Because we have the extra information that it's completely antisymmetric. Okay. This means that if you interchange any 2 indices, alright, so what I said that epsilon 1, 2, 3 is equal to 1 and the fact that it's completely antisymmetric about its indices. Completely antisymmetric about its indices means that if you interchange any 2, you get a minus sign. This means that epsilon 2, 1, 3 is equal to minus 1, etc. So this is the only thing you need to remember basically. Okay, so if you confuse between cyclic, non-cyclic, you remember that epsilon 1, 2, 3 is 1 and the fact that it's completely antisymmetric about its indices. So that will give you all the possible things. Right, now using this we can write the result. We can write the result Li with Lj. Alright, so here instead of Lx, Ly, Lz, we are saying L1, L2, L3. Alright, instead of Lx, we are saying L1, instead of Ly, we are saying L2, etc. Okay, Li with Lj is epsilon I, j, k, Lk. Alright, remember we are using Einstein summation convention, so this means that you have to sum over k. Alright, how do we check this? For example, this means that if you put I equal to 1, L1 with L2, what do you get? It's epsilon. This I have put 1, so here also I have to put it 1. This j I have put 2, so here also I have to give 2. Okay, and you have to sum over k. You have to sum over all possible values of k. Right? But if I put k equal to 1, this is epsilon 1, 2, 1 and it's 0. If I put k equal to 2, it's epsilon 1, 2, 2, which is also 0. If I put k equal to 3, it becomes epsilon 1, 2, 3, which is equal to 1. So that's only non-zero value. So it's epsilon 1, 2, 3, L3. And what's epsilon 1, 2, 3? It's 1. Okay, so we get back the result. L1 with L2 is equal to L3. Okay, so this is an elegant way to write down the angular momentum Poisson bracket results. Okay. Now, Li, what's Li? It's the ith component of the angular momentum vector, right? The Poisson bracket of any system vector, A vector, right? So this is actually true for all vectors, all right? This is actually true for all vectors, which we don't prove here, but I am giving it to you as a result. This is actually true for all vectors, all right? If you take any vector, and take the Poisson bracket with angular momentum, it follows this result. All right. So what we saw was Li with Lj is equal to epsilon ijk Lk, summation implied. Okay. All right. This means that Li is actually the ith component of a vector. This is actually the property of all vectors. You can substitute any vector here. So Ai with Lj is epsilon ijk ak. Right, epsilon ijk ak. Okay. This is an important result and it has to do with the fact that angular momentum is actually the generator of rotations. All right, angular momentum is actually generator of rotations. All right. Okay, it's also true that you can also write it that Li with Aj is epsilon ijk ak. Right, you can show this. You can use the antisymmetry property of epsilon ijk and actually show this. Right? So the angular momentum Poisson bracket with any vector follows this rule. Okay, and it's a deep fact of nature. It's because it's actually a property of all vectors. All right, if you take any vector and take the Poisson bracket with angular momentum, it follows this rule. Okay. Now, if you remember this, some of the problems can be solved very easily. Okay, and we'll see that this particular result has to do with the fact that angular momentum is actually a generator of rotations, and we know that all vectors transform under a particular way when you make rotations of coordinate system or something. Okay, so I hope that's clear. If you don't know all those details, it's all right, but I want you to remember this result. Okay, it's important. All right. Okay. Right, so I think I shall just prove this here. Okay, we have got this result AI with Lj is epsilon ijk ak. Right. So what's Li with Aj? Li with Aj. Okay. So we say that this is equal to minus Aj with Li. Fine. And we know Aj with Li from here. Okay. It is epsilon j I k ak. Alright, it's epsilon j I k a k, but there's a minus sign here. Alright, now what do? I can interchange these indices and you'll get an extra minus sign. This is equal to plus epsilon I j k a k. Alright, that's the result. That's the result that I have written here. Right, I hope that's fine. So I want you to remember this. This could be any system vector. It could be the momentum, it could be the position vector, it could be any vector related to the physical system, and this result always holds. Okay, so if you are asked some Poisson bracket with the angular momentum, and if it's a vector of the system, then you remember that this result can be directly used. Okay, you don't have to go to the trouble of looking at all the components of the angular momentum and then doing all these things and finally finding that this indeed is the answer. You can make this shortcut to get to the answer. So this is one of the shortcuts that we can use in the competitive examinations. Okay. So we have looked at some examples. Let's do some problems now. Okay, some of them will leave us exercises. So this is u with v square. Okay, show that u with v square is 2v u comma v. This is quite easy because we can say u with v square is simply u with vv. And now we can use the product rule. So this is u comma v multiplied by v plus v multiplied by u comma v. This is the result that we have seen before. All right, this is like a comma bc. It's ab multiplied by c. Sorry, a comma b multiplied by c plus a comma c multiplied by v. All right. So this is exactly the same term because the order does not matter. So it is 2v u comma b. An important result. All right. Now we can actually do this in the examination, but this is one of the results. If you remember, it's not very difficult to remember. It looks something like taking the partial derivative or something. But if you remember this result, you may be able to save some time. Right? Similarly, in the same manner, u square with v is 2u u comma v. Obviously, okay, you can check this actually. Now there's another result that we are asked to find. What's the relation between the Poisson bracket u comma v with the Poisson bracket u square comma v square? Right? We are asked to prove that Poisson bracket u comma v is Poisson bracket u square comma v square divided by 4uv. This is not particularly difficult. We can use the previous result. So let's start with u square comma v square. Right? Now remember that there's a v square here. So this is 2v square multiplied by u square comma v. Okay, we have used the previous result, but we can use the previous result once more. So this means that it's 2v square and then 2u square multiplied by u comma v. All right, I'm just using the previous result here. You can check. Okay, so this is actually, sorry, there's no 2v square, it's 2v. I'm sorry, the previous result said that u with v square is 2v u comma v. I apologize. All right. So you have got u square comma v square. So you first consider this term. So it's 2v u square comma v, and then this is 2u. This is simply 2u multiplied by u comma v. Okay. So it's actually 4uv multiplied by u comma v, which means that u comma v, the Poisson bracket u comma v, can be written in terms of the square of the terms in here, or the square of the functions in here. So it's Poisson bracket of u square comma v square divided by 4uv. Okay. You can think of it as a problem, or we can think of it as a convenient result that you need to remember. Right? It's up to you. It may help in solving some of the problems. And here is a problem that was asked for the net exam, one of the net JRF exams. All right. So this is a previous question, previous year question. Okay. So you are asked to find the Poisson bracket modulus of r vector comma modulus of p vector. Modulus of r vector comma modulus of p vector. Alright. So what's modulus of r vector? It's square root of x square plus y square plus z square comma square root of px square plus py square plus pz square. Okay. Now one way to do this is to use the fundamental definition. Alright. If you have something like u comma v, this means that it's equal to dou u by let's say dou qk dou v by dou pk. Remember there's a summation here, minus dou u by dou pk dou v by dou qk. In this case this becomes because qk, q1, q2, q3 are x, y and z. So this becomes dou u by dou x dou v by dou px plus dou u by dou y dou v by dou py plus dou u by dou z dou v by dou pz minus by interchanging, minus the three terms by interchanging x px, y py and z pz respectively. Okay, that's one way to do that. All right, and you may actually try that. All right, try this using definition. All right, but the problem, the way I have solved here is slightly different. I will not use the fundamental definition of the Poisson bracket. Instead, I will use some of the results of instead I will use the fundamental Poisson bracket relations. The fact that I will use the fact that x with px is 1, y with x with x, x with py, py with px, all these are equal to 0. Okay, this fact can be used. All right. Okay, so here we have got square root of x square plus y square plus z square plus square root of px square plus py square plus pz square. Right. Now we can use the previous result. What was our previous result? It said that u comma v is equal to u square comma v square divided by 4uv. That's exactly what we'll do here. We'll find u square comma v square and divide it by 4uv. Right. And what's u square? This is u and this is v. So u square is x square plus y square plus z square comma px square plus py square plus pz square divided by 4uv. Okay, in the place of u you have got square root of x square plus y square plus z square, and in the place of v you have got square root of px square plus py square plus pz square. Is this clear? I hope that's clear. Okay. Now what do? Now we have to take, you can use the distribution rule and take all the Poisson brackets. Alright, so you have to take x square plus with px square plus x square with py square plus x square with pz square. Similarly, y square with px square, y square with py square plus y square with pz square, etc. You have to take all the terms. Okay, but you can make use of the fact that most of these are actually 0. All right, so from the fundamental Poisson bracket relations, we know that x with px is non-zero, but x with py is 0, x with pz is 0. Right? So you only need to take the non-zero Poisson brackets. That simplifies things for us. Okay? So if you take the non-zero Poisson bracket here, you'll have x square with px square. That's only non-zero term. Similarly, you'll have y square with py square. That's only non-zero term. Similarly, z square with pz square. All other terms are 0. Okay, that's exactly what we'll do here. It's x square with px square plus y square with py square plus z square with pz square. Right? So remember, we have used the fact that qi, okay, we have used the fundamental relation that qi with qj is equal to pi with pj is equal to 0. All these are 0. Similarly, if you have qi with pj, it can be non-zero given the condition that I is equal to j, which is to say this is equal to delta ij. All right, you remember this, I hope. Okay. So if these are different, if you have something like x with py, it's 0, but x with px is 1. All right. Now you've got x square with px square plus y square with py square plus z square with pz square. Okay, divide by 4r vector p vector. Why? Modulus of r vector, modulus of p vector, because we know that this is modulus of r vector and this is modulus of p vector. Okay, all right. Now we already found that u square plus v square, u square with v square, we have already seen in one of the previous problems that u square with v square is actually, what's it? It is 4uv multiplied by u comma v. Am I right? I think we proved this. Okay, so this is 4xpx. So this is actually the first term I will do. It's 4xpx multiplied by x comma px. And what's x comma px? It's 1. All right. These are the fundamental Poisson bracket relations. These are known as fundamental Poisson bracket relations. X comma px is 1. All right. So it's 4xpx plus 4ypy plus 4zpz. Right. Now what is this xpx plus ypy plus z? What is this xpx plus ypy plus zpz? It's simply r vector dot p vector. Am I right? R vector dot p vector is xpx plus ypy plus zpz, and this 4 will cancel with this 4. So you have got r vector dot p vector divided by modulus of r vector, modulus of p vector. Right? So r vector by modulus of r vector is simply r cap, the unit vector along r direction, and p vector divided by modulus of p vector is simply p vector cap.